Alright, let's talk about using the inverse of a Laplace transform. Say I had the function f of t equals e to the alpha t. We know the Laplace transform of that is equal to 1 over s minus alpha. So what if I'm given this formula right here, this equation right here, saying I'm giving you some L of s. What was the function, the f of t, that I started out with to create this? In this case, I started out with e to the alpha t. So if we create a table here, f of t and a L of s column, we know that any constant c we put in, the output will be c over s. If we're given any t to the n, we're going to get n factorial over s to the n plus 1. We know that given some e to the alpha t, we're going to get 1 over s minus alpha, and there's the trig ones. There's one more that we looked at, which was just given some y prime or f prime of t, you end up with s L of s minus f0. So if I gave any of these L of s, say I started out with 3 over s, the f of t would have to have been 3, because if I take the Laplace transform of 3, I get that same constant over s. So you can work it out one way or you can work it out the other way. This is useful because you can use Laplace transform to solve differential equations. One example is y prime plus y equals 0. This is a differential expression. If we translate this into the appropriate Laplace transform, solve that Laplace transform for some L of s, we could potentially find some function of t that's would have to be a solution to that transform. Basically, convert this, solve it, and then convert it back to find y. A way that we can do that is just replacing each element of this expression with its Laplace transform, and we know how to do that for each of these pieces. Y prime is just f prime of t, and like I said here, that comes out to s times L of s minus some starting condition, and that's all this first part of the equation. And then we're adding, let's take the Laplace of y. Well, what is that? The Laplace of y is just the Laplace transform of y, so it's just L of s. And the Laplace of 0 is just 0. It's it's a constant, so it's 0 over s, which just results in 0. So what we can do now is add f0 to both sides and factor out the Laplace transform. You end up with s plus 1 L of s equals f0. And I could divide both sides by s minus 1 and come out with L of s equals f0 times 1 over s plus 1. So we have a Laplace transform of some function f of t that resulted in f0 times 1 over s plus 1. So what f of t could have been used? We know that the Laplace of e to the alpha t equals 1 over s minus alpha. If we compare these two, if we set alpha to be -1 at f of 0, we would get 1. So that would follow that f of t equals e to the -t. If we look at the initial differential equation, it said y prime plus y equals 0. If we check this, we're saying that e to the -t, negative e to the -t, plus e to the -t equals 0, which it does. So we have found a solution. E to the -t is a solution.